Good. So we're now moving into two talks on kagome materials. One is now and one is after the break. And our first speaker on that topic is Linda Yi from Stanford.
Thank you. I hope you guys can hear me in the back. I think the microphone is working. First of all, I'd like to thank the organizers for having me here. And today I'd like to talk to you about flat bands in this set of materials called kagome metals. And since the theme of this conference is topology, symmetry, and interaction in crystals, hopefully through the talk I can convince you that maybe this lattice approach with a little bit degree of freedom of the orbital can be an interesting way to connect some of those concepts. Right. So before I go to the talk, let me very selfishly advertise for my new group, which is going to start in the fall of this year. And it's at Caltech, which is 2 hours drive from here. And we're really interested in exploring new quantum materials through the perspective synthesis and transport thermodynamic measurements. So this is a photo that's taken from the direction of the physics department. So I hope I can come back to visit KITP with a relatively short drive. So before I go into the physics, let me also thank my colleagues and collaborators, without whom the work I'm going to present to you today wouldn't be possible. So I'd like to, first of all, thank my PhD advisor, Joe, here. And among everybody else, I would like to really highlight Minggu Kang from Ricardo Cummings' group, and Shangfang here, who's now a postdoc at MIT, for establishing the photo emission and DFT understanding of this class of compounds I'm going to show you today. Right. So I'd like to start by making some really general statement about flat bands, since it's a slightly counterintuitive concept. So you might have thought about those questions yourself, but I wanted to just really flash some of those notions here. So let's first start by thinking about dispersive bands, and this is dispersive bands for the tight binding model on a really simple square lattice. And the eigenwave function of this tight binding model would be these Bloch waves that's extended across your entire crystal, and this energy momentum dispersion of this hopping Hamiltonian would give you the band structure. Right. So now let's think about a band artificially without any energy dispersion, which we call a flat band. So although here we still label the states using momentum, since if you recall from quantum mechanics, since all these states here are degenerates, if you make linear superpositions of degenerate states in a degenerate manifolds, you can get the eigenstate of the original Hamiltonian. Right. So this would allow the flat band to have both real space and k-space eigenwave functions through the Fourier transform. And you will see that we base a lot of our discussions of the flat band on the localized wave functions. And right, so this already gives you some flavor of localization in the flat band states. And the second thing I want to mention is that because the energy scale here, the band as flat, so any interaction you add to this manifold would not be a perturbation, and as a result, it's a really good platform to study different kinds of emergent phases, right? And also, I want to mention that a sort of a trivial way of making a band flat is to simply turn its hopping parameter to 0, and then we get a set of isolated atomic states. And I want to mention that the flat bands we're interested in is slightly different from this. And I hope it can become more clear what I mean as we move on. Right. So maybe the last comment I want to make here is that in real life, it's really hard to have a band that has absolutely no energy dispersion. So therefore, when we are talking about the flat band, we are really saying that they are flat with respect to other underlying interaction strengths in the system, such as electron-electron interaction or electron-phonon interaction, or etc. Right. So up to now, the flat band physics has mostly been discussed in the lambda levels at high magnetic field in two-dimensional electron gas, and also in the van der Waals superlattices, where you get the flat band from the Moiré superlattices. Right. So indeed, you can see a lot of interesting emergent phases in those systems, including fractionalization and superconductivity and symmetry breaking phases. So here we wanted to ask the question whether you can find flat band states in the bulk single crystal systems, which combines the rich possibilities of three-dimensional crystal structures and the periodic table. Right, so one motivation of looking for flat bands in this approach is that potentially we can find flat band physics happening at relatively high temperatures if we can make use of the already correlated nature of some of the D or F elements. Right, so this is sort of our goal to find a flat band in three-dimensional crystalline materials. And our starting point would be to focus on this set of ideas that one can make flat bands using certain geometry of lattices. So first of all, I want to just spend a few minutes going through some of the ideas of making flat bands using lattices, and then I will be focusing on this class of materials that has one of the flat band hosting lattices, and namely the kagome lattice. And we'll see whether we can find flat band in those systems and what kind of emergent properties they will give us. Right. So, right. So this is one of the, this is the earliest idea of making a flat band using a lattice. So this is from B.O. Sutherland around 30 years ago, and it's based on this lattice called the dice lattice, right? And if you do a tight binding model on this so-called dice lattice, you can find a flat band at zero energy that's across the entire two-dimensional Brillouin zone. So it's really easy to mistaken this as the zero line of this plot, but it's actually a flat electronic band. And here is an illustration, and I want to mention that although this is a relatively old idea, there's a sort of a renewed interest in this flat band induced the flat band hosting lattices because of their potential, because of their the connection to band topology. And I'll borrow these illustrations from both the old and some of the relatively modern literatures. So this plot on the top left is an illustration of of the real space eigenwave function of the flat band on the dice lattice. And you can see that this is a 6-site wave function that's evenly distributed among these 6 sites. And there's an alternating sign pattern across the 6 sites. Right, so starting from this wave function, any hopping from a pair of the 2 sides would be destructively interfering with each other and cancels out. And therefore, this particular form of wave function confines itself within this 6 sites, and as a result, this gives us the flat bands. So in some sense, what is needed here is a certain kind of lattice geometry that that supports this sort of destructively interfering wave function. Right. So you might have noticed that the dice lattice itself, as a two-dimensional model, is sort of artificial, because if you look at the sites 2 and 3, they look pretty close to each other, but you actually don't draw a bound in between them. So instead of focusing on the dice lattice, we're going to focus on a different two-dimensional lattice model called the kagome lattice. So this lattice is composed of corner shared triangles, and you can view this as starting from a triangular lattice and take away the center atom in the hexagon. Right. So the nearest neighbor bounds in the kagome lattice naturally gives us this frustrated network, and this supports a flat band either at the top or at the bottom of this set of 3 bands, depending on the hopping parameter. Right. So this looks a little, and we believe this would make it easier for us to find this lattice in real materials, and this is what we are going to focus on. And in this slide, I want to very briefly show you the strategy we took to sort of systematically search for candidate compounds that has the kagome lattice in their 3-dimensional crystal structure. So we started from a single kagome layer, and we tried to imagine how we would stack them up in a 3-dimensional crystal structure. And the simplest 3 ways of stacking them up in a 3-dimensional crystal structure are the AA, AB, and ABC. And this would give us 3 different space groups, 191, 194, and 166, even if we don't think about any additional atoms in between those layers. Right. So we went into the inorganic crystal structure database with those space group numbers to narrow down the candidate materials that has the kagome lattice in their crystal structure. So this led us to some of the interesting structures where you can find a lot of different other elements you can stuff in between the kagome lattice of the transition elements. But in our experiments, we're going to focus on the chemically simplest class of binary compounds that has the kagome lattice. So this is these are those kagome lattice hosting binary compounds. And here I'm only showing you the compounds between iron and tin, but you can easily imagine replacing iron with another transition element and tin with another main group element. Right, and there are 3 different compositions, 1, 1, 2, 3, 3, 2, sorry, and 3, 1, which indeed have the 3 different types of stacking we just saw. Right, so the fundamental building blocks of this class of compounds is this iron-3 tin kagome layer and this honeycomb layer of tin. And if you stack those kagome layers right on top of each other, you would get a AB stacking as in the 3-1 structure. And you can also stack them across the spacer layer that's made of this honeycomb lattice. And this would give you the AA stacking in the 1-1 structure. And the structure in the middle gives you a mixed AA and AB stacking. And overall, it actually has a ABC robohedral type of stacking. Right. So I want to mention the materials detail that the number of isostructural compounds for those 3 different compositions are quite different. And we will actually come back to this point a little bit later. So this is some pictures of the compounds we have grown that has those 3 different structures and 3 different crystal structures, right? And the elements that compose the kagome lattice is highlighted here in the periodic table, which is a little bit hard to see. So nevertheless, you can see that a lot of those crystals have the hexagonal morphology, which reflects the underlying hexagonal symmetry of the kagome lattice. Right. So first of all, I want to very quickly show you that we indeed can find flat bands in 2 of the isostructural compounds, iron zinc and cobalt zinc, in photo emission below the Fermi level. So in both cases, you can see that there's a flat dispersionless mode that's below the Fermi level, around 200 milli-electron volts in the 2 cases. Right. So, here I want to just show you the origin of the flat band in cobalt zinc, where we believe we have a relatively good DFT understanding of this flat band. So this is the one-year wave function of the flat band here, which has this this hexagonal state that's composed of the d orbitals on the rotated basis, right? So more or less, you can view this as a d orbital generalization of the s orbital destructive interference we looked at slightly earlier, right? So at least it seems that this class of compounds and also the lattice approach of looking for flat bands in those materials could be a good starting point to give us flat bands in their electronic structure. So the next question would be that's whether we are able to bring the Fermi level to the flat band and really start to see some correlated electron physics. So one way of doing this is to, for example, hold dope cobalt zinc to really bring the Fermi level to the flat band, because doping always introduces disorders. So what we wanted to do is to find a stoichiometric material that has a flat band at the Fermi level. So instead of doing the whole doping here, we actually went back to the binary compounds, and we went back to the stacking pattern that has the most number of materials, and see if one of them would actually give us the flat band at the Fermi level. Right. So this would bring us to the system I really want to talk to you about today, which we believe we managed to bring the flat band to the Fermi level. And the material itself has the composition nickel-3 indium. So instead of tin, you have indium in the center of the hexagons of the kagome lattices. And in a unit cell, there is an AB stacking of the kagome lattices on top of each other. And the stacking pattern can be seen pretty clearly if you do a cross-section using TEM of the atomic structure. Right. So on the right is the DFT band structure of this material, and you can see that the most prominent feature in the band structure is that there is a flat dispersion that crosses the entire in-plane momentum that's right at the Fermi level. Right. And there are also other dispersive bands in the system. And this is a magnified view of this flat electron band in the AB plane. And you can see that the single particle states are partially filled. And the overall bandwidth is on the order of 60 milli-electron volts. So this is a SEM image of some of the crystals we grew in our lab, which you can see that it has the hexagonal morphology. Right. And with these crystals, we can do transport and thermodynamic measurements. And this is the in-plane transport of this material, where we can see that, roughly speaking, below 100 Kelvin, the resistivity behaves linear in temperature, and it starts to roll over at higher temperatures. Right. And we can make a really simple comparison of the Roti curve here with the Roti curves of the other compounds in the same structural family. And so on the right are the Roti curves of some of the other kagome metals we have grown in our lab, and some of those materials, iron 3 tin, iron 3 germanium, and nickel 3 tin, has the same crystal structure as nickel 3 indium, but the difference here is that everything on the right doesn't have a flat band at the Fermi level. So the difference, you can see that on the right, when you don't have a flat band at the Fermi level, no matter whether your underlying magnetic order is ferromagnetic, antiferromagnetic, or non-magnetic, you always see this similar Roti behavior, which is linear above 100 Kelvin and starts to roll over below 50 Kelvin. Right, so this is a pretty conventional Roti curve that comes from electron phonon scattering. And from this comparison, right, you can see that the nickel 3 indium actually is a pretty special member of the family, and this unconventional transport response has to come from the fact that the system have a flat band at the Fermi level. Right. So this slide is basically showing you what the Roti curve in the system doesn't look like, and in the next slide, I want to just show you a phenomenological comparison of what the Roti curve looks like. Right, so there are two systems I want to compare to. The first one is the gold-doped cerium copper-6 at antiferromagnetic quantum critical point. So in this plot, let's just focus on the circles, which is taken at zero magnetic fields. So here you can see a linear dependence below 0.5 Kelvin, and it rolls over, right? And another system I want to compare to is the phosphor-doped barium iron arsenide, which is close to the optimal doping. Right, it's also a critical composition, and you can see a similarly behaving Roti curve. Right, so there seems to be a phenomenological comparison across the systems, despite the very different energy scales, temperature scales, and also the very different underlying materials. Right. So here, if we look at the low temperature part of the Roti curve, if we go to geofridge or helium-3 temperatures, we can see that the system recovers T-square behavior at low temperatures. And with this, we can do a Kadawaki-Woods analysis. So what this does is to take the ratio of the A coefficient of the T-square dependence and the square of the Sommerfeld coefficient in heat capacity. So what this analysis does is that since A is sort of the scattering rate in the system, and gamma, the Sommerfeld coefficient, can be used as a proxy of the density of states in your system, right? So taking the ratio sort of takes away the effect from density of states and should give you some insight on the underlying scattering mechanism in your system. So if you plot A and gamma in the log-log plot, each of the straight line would represent a different value of the Kadawaki-Woods ratio. So what we find is that nickel 3 indium is here, and its Kawasaki-Woods ratio is orders of magnitude larger than what you find in the elemental transition metals, and it's closer to some of the more correlated materials. So in some sense, this gives us more quantitative indication that the scattering process in the system is unconventional. Right. So to gain a little bit more insights in what's going on in the system, we applied magnetic field and pressure as external tuning parameters to the system, and we tracked the evolution of the resistivity power law in the temperature field or temperature pressure planes. And what we found here is that both field and pressure tend to increase the resistivity exponent at low temperatures, and it gives you a larger region of alpha equal to which you get a Fermi liquid phase, right? So if we plot this in the schematic, we have a field and pressure induced crossover between the non-Fermi liquid behavior and a Fermi liquid behavior, right? So this motivates us to propose that perhaps our system is located somewhere not super far from a potential ordered phase through a quantum critical point. So we are likely here, and both pressure and magnetic field tends to actually drag our system away from this potential quantum critical point. So we still experiences some of the residue quantum fluctuations near this region. Right. So up to now, I have been the discussion has been more or less phenomenological, and in the remaining few minutes, let me just give you a picture of what we think is going on in our system. Right. So if we look back at the DFT band structure of the system, you can see that there is a coexistence of flat electronic bands and other dispersive bands near the Fermi level. Right. So this would remind you of the band picture you can draw for some of the heavy fermion compounds, where before you turn on the hybridization between the conduction electron and the localized F moments, right? And this is a schematic I took from this reference for cerium, cobalt, indium 5, right? So there, the F electron are represented by this flat band at the Fermi level that's below, with the width below 20 millielectron volts, right? So the heavy fermion systems is a very well-known system that hosts quantum critical points due to underlying competition between the tendency of the conduction electron to fully screen the local moments, therefore forming a heavy Fermi liquid, and the tendency for the local moments to order themselves, forming this magnetic ordered phase through a quantum critical point. Right. So perhaps we can borrow some of the wisdom that's gained from the study of heavy fermion systems to understand what is going on in our system. So we are still not at the position to really pinpoint ourselves to the exact location in this schematic, but we did some initial a calculation to sort of help us understand better what is going on in these flat band systems, in the flat bands in the system, right? So here I wanted to show you a magnetic susceptibility calculation we did for the compounds without taking into account of interaction. So what we did is that we did a tight binding fitting of the flat electronic states at the Fermi level, and from this tight binding model, we calculated the temperature dependence of the spin susceptibility. So what we see here is that there is a rise of the susceptibility as a function of temperature. So this is a funny axis for temperature because it's in milli-electron volts, right? So this is just a calculation. And you can find that the rise actually can be described by a Curie-wise temperature dependence. And this has been discussed as a signature of a pre-formation of magnetic moments in systems where before taking into account of interactions. Right. So here I wanted to show you our experimentally measured magnetic susceptibility as a function of temperature. So above 80 Kelvin, we can also fit the chi-T with the Curie-wise. And so this is consistent from the expectation from the calculation where we could have magnetic moments in our system. Right. I wanted to very quickly note that we found a deviation of the magnetic susceptibility from the simple Curie-wise starting from 80 Kelvin, and we don't have a good understanding of the origin of this actual deviation yet. So another comment I want to make here is that the comparison between theory and experimental here is actually not quantitative, because if you convert this milli-electron volt to temperature, those are actually temperatures that's too high for us to achieve experimentally. So the comparison here is more qualitative, but I hope it gives us a starting point to maybe think about think about the system as the coexisting local moments coming from the flat bands and the conduction electrons coming from other dispersive states in the system. Right. So I think with this, I'd like to conclude our talk. So I hope I have shown you that the kagome lattice metals can be an interesting material platform to look for flat band states, and by bringing the Fermi level to the flat band, we are able to see some pretty unconventional transport behaviors and aside from answering, I have to say that our understanding for what's going on in this compound is still preliminary, and that we really hope to maybe borrow some of the wisdoms from the heavy fermion community to help us understand what's going on in our system. So aside from, for future directions, aside from trying to answer the open questions in the material system itself, I'm also super excited to see maybe more broadly this lattice-based flat bands to be studied in more material systems. And I'd like to highlight one of the works from the group of Andrew Bernavik on the DFT on categorizing candidate materials to study flat bands in stoichiometric crystalline materials. So with this, I'd like to thank you for your attention and take questions.
Hi, thank you very much for the talk. I have a long list of questions, but let me start with the first one. So bringing the flat band to the Fermi levels, yes, we understand that's very important. Do you have any insight how to guide us to search for those materials? Because you said that in the group that you were searching, there are like about 200, cases to consider. So how did you end up with a nickel-free indium, and what is special about it? What is required to bring them to the Fermi level?
I think, in some sense, so what we found is that, there's, if you look at those band structures for a long enough time, you might find that a lot of those band structures look similar, but different materials have a different Fermi level. So in some sense, the nickel-3 indium just happened to have the Fermi level at the flat band.
So was that band structure published before you chose to synthesize it, or?
So it was available on a lot of the band structure databases, for example, the materials project, and okay. So you can find those in some of the databases. I believe there are more than one database at the moment you can.
And did you look at it experimentally using ARPAS?
Yes, we have ARPAS data. So, sorry, I didn't include it in this set of slides, but I can show you afterwards.
Probably other people want to ask, but I can ask later.
We'll come back to you if there's more time.
Hi, I was wondering, did you look at the Wilson ratio? So comparing the susceptibility and the specific
Yeah, that's
heat?
a good question. I think so. In some sense, yes, we did, and I think we got a number that's on the order of 10.
Okay, so it sounds like it's close to ferromagnetism.
Right, but on the other hand, I don't know if I really understand the temperature dependence.
I mean, it's higher than the Curie-Weiss fit. So if you were going screening your moments or forming antiferromagnetism, you would expect it to be lower. So that makes sense to me that it's something near ferromagnetism.
From the Wilson ratio perspective,
No, am I wrong? Okay.
I would think that the heavy fermion mass increase can typically look like that even in an antiferromagnet, because you get a very large constant. If you zoom in, if you plot it on log scale, you can of course deviate to the positive in a heavy fermium antiferromagnet, because you have a very strong Pauli susceptibility, and then it will level out at low temperature. Right? You start Curie-Weiss at high temperature, and you deviate to the positive to go to large Pauli. You don't think so? I think it's standard.
We're actually, yeah.
Yeah, but I don't think it tells you a priori anything about ferro or antiferro. It could just mean the mass gets enhanced. No? Okay.
Yeah, we are also extending our magnetic susceptibility to low temperatures, so that can tell us more.
Yeah, so I had a question regarding the slide actually right here. Okay. So the constraint of a flat band for the kagome comes only to be within the plane, right? The geometric flat band is only within the plane.
That's correct, yeah.
And so outside the plane, there is no such lattice-based constraint.
That's right, that's right.
Now, so my question is, have you looked at, for example, the resistivity out of plane to see if there is any non-Fermi liquid-like behavior or any correlation effect?
Yeah, so I think we've looked at that, and I didn't have the data here, but I think we found a higher conductivity along the C-axis.
I see.
And there's a weaker, in general, weaker non-Fermi liquid behavior in the C-axis, so which makes sense from this.
Right, and also
this perspective, right?
Right, and also this deviation that you get from this preformed local moment picture, can you understand it from the third dimension, the fact that you have a dispersion, or?
I don't know about that.
Okay, okay.
Yeah, I think it's an open question. Yeah.
Hi, thanks.
Hi.
Thanks for a nice talk. I had a question about, so this, in the nickel compound, you were able to bring the chemical potential close to the, or the flat bands close to the chemical potential. The other ones which were where the flat bands were somewhat away, did you also see local moment formation within those flat bands? Because, you know, flat bands would become susceptible to forming local moments, and even if they are away from the chemical potential, they could still influence the electrons at the chemical potential.
So we haven't seen those, let me see, let me go to that slide first. So we haven't seen too much signatures of local moments in our own experiments, but I believe there's actually a report on cobalt-zinc from the Oak Ridge group where they did magnet to resistance, and they saw a negative magnet to resistance of this compound at very low temperature, and they were attributing that to perhaps a formation of magnetic moments in those systems. Yes.
That's super indirect. So why not just measure susceptibility? Is that Curie-Weiss, yes or no? That's a simple question.
Like.
It's not Curie-Weiss?
It's probably like in this compound. So
okay.
I don't fully understand.
Okay. So I have a second question. So you argued in your Kadowaki-Woods plot sort of about reading of different scattering mechanism, but I mean you are in the situation that your A coefficient, which you measure in the plane, measures only the heavy masses, but your specific heat averages, right? Because you measure. So isn't that a much more obvious explanation?
I see.
So in some sense, your gamma is too small for your A, right?
Let's see.
Is it? Yes, it is.
Right. So I guess. Okay. So maybe we'll look at that more carefully, but maybe that would give us a lower bound. Maybe an upper bound of gamma in some sense, or
yeah, you measure the lower bound on gamma, definitely. I think so. Your point might move to the right if you could measure only in the plane.
Right. Yeah. Yeah. I don't know how far, how much it would influence this.
Maybe just to the green line.
Maybe not like 3 orders of magnitude, right? Okay. That's a very interesting point, thanks. Oh, yes.
So what's the Debye temperature in your material?
Debye temperature from the heat capacity, I think it's on the order of 300 Kelvin.
300?
300, I think so, for this class of compounds, yeah.
Okay, so it's much greater than the crossover temperature between linear and quadratic.
Yeah, I think, if my memory is correct, the crossover happens like 1/5 of Debye temperature in general, I think. So above 1/5 of the Debye, you see a linear in T, and below 1/5 of Debye, you see a crossover. And I think this is what's happening in the other compounds, right?
Oh, okay, so in all of these compounds, you would say it's unconventional.
Oh, no, sorry. Are you asking the phonon, the Roti curve from scattering between electrons and phonons? Or?
Well, I expect a temperature much greater than Debye than linear in T is expected.
From the phonon electron scattering,
yes.
Right? And this is what's happening, I think, in the other systems, where above 50 Kelvin, you have a T-linear resistivity that comes from phonon, right?
And if the T-linear extends below T Debye, then I would think that's unconventional.
Right. I think what I'm showing on the left is unconventional because it extends below Debye, right?
Okay, sure. Right. And on the right, it does not.
On the right, it does not. So those are the conventional cases, and left is the more unconventional case, I think.
Okay, thanks.
Cool.
But if in the end, if you go to lower temperature, you say that it's more like T square.
Yes.
And, when we talk about non-Fermi liquid behavior, you think about the, 0 Kelvin behavior. So would you still call this non-Fermi liquid if it
in some sense, at the 0 temperature, it's not a non-Fermi liquid, right? So it's Right, so I guess it's still crosses off a phase diagram like this. So at lowest temperature, yes, I don't think we should be calling it a Fermi liquid behavior, but above that there's a deviation from.
Do you have any Hall effect or magnetoresistance?
Yes, I do. So the Hall effect, we don't have a super good understanding of what's going on here. So I guess this is the temperature dependence of the Hall coefficients with field along C, and this is the in-plane Hall coefficients as a function of temperature. Right, so there is indeed a rise of the Hall coefficient as a function of temperature, which sort of resembles the magnetic susceptibility, but we're not sure the origin of this rise yet. And this is what we measured if we bring the system to higher magnetic field. So there's actually a more complex structure in the Hall effect, and it's actually rose over at higher fields, which might be related to field-induced Fermi surface change, but we don't have a good picture yet. Yeah.
Thanks for the very nice talk. I want to understand. I want to understand the motivation for thinking of the interactions in terms of a Kondo picture rather than a generalized Anderson model kind of picture. So if you go back to the slide in which you showed the experimentally measured Curie-Weiss susceptibility, the deviations appear to be the exact opposite of what you would expect when Kondo hybridization sets in. You would expect a crossover to Pauli susceptibility. I'm wondering, so to motivate a Kondo description, there is a requirement that the interactions, when you project them onto these flat bands, must be stronger than when you project them, not the dimensionless, but the dimension-full interactions. Is there any reason to believe that these projected onto the flat bands would be stronger than projected onto the conductions?
I think that's a good question. So I guess in some sense your question is that if we have so the magnetic susceptibility for a like a single Kondo impurity should look like something like this, right? It should come down because of the screening of the local moments. So I guess I was being a little bit loose here. So when you have a Kondo lattice in the system, so in some sense that's the case when you're in this region where you have a well-formed Kondo singlet at low temperature, right? So in some sense, we don't know where exactly we are in this Doniak type of phase diagram. If, say, for example, if we are closer to where there's a competition between the screening of the local moment and the local orders, the susceptibility behavior might not be as simple as what you expect for the screening of the moments. Yeah.
I see. So I think in terms of the evidence for local moments can occur in a variety of strongly correlated models. But why Kondo?
Is that a question?
Okay, so I think we should move to the coffee break, and I'm sure Linda would be happy to answer other questions then. So thanks for a great talk.
Thank you.